Okay, so I'm going to go ahead and get started. I'm excited today because we have a couple of presenters that are going to be presenting two different tools. And then the other topic we're going to have today is kineticEFITtime. And I'm excited about that. Brian Victor is going to be talking about that. He's a Lawrence Livermore National Lab scientist. He deals with steady state and advanced tokamak scenarios. And he's been, one of the aspects that he brings to it is he's a user of kineticEFITtime, a really strong user. And so he'll definitely give you a perspective from that perspective.
All right, so now I'll go through my process for doing kineticEFITs. Feel free to ask questions anytime. I'd rather prefer answering questions than just talking. All right. So I typically just use the stable branch of OMFIT. Unless it doesn't work for whatever reason, then I'll switch to the unstable branch. But as Will mentioned in the introduction, I'm typically more of a user. I've done a little bit of development, but not very much. So I try to use this as a tool more than doing a lot of my own development. So when you get this screen, probably all of you are very familiar with OMFIT, but I always start with import module, unless I'm opening a past project. And then this filter works great. So you just start typing the module you want to load, and then you can double click on kineticEFITtime. So I'm going to look at high Q min shot because those are the kind of shots I tend to analyze a lot. So when I start this process, I want to choose times that I think will work well for the diagnostic. So as a MSE diagnostic person, I look for times when there's MSE data because that's an important diagnostic for these kineticEFITs. So what I have shown here are the time traces for 30 left and 30 right. So to get MSE data, you need 30 left on and you need 30 right off. Whoops. So the black trace is 30 left and the red trace is 30 right. So I'm looking for these sorts of times right here where you have 30 left on and 30 right is off. So in this case, I'm going to choose like every 100 milliseconds. This is 29:45, 30:45, 31:45. And I'm going to use these times within OMFIT. So double click here. The shot I'm analyzing is 195646. When I put in the time range, I almost always click in this double dot region, and that allows me to use Python commands. So I can type a range and then give the start time and then give some time after the end time and then the delta t. So I use that, I hit update, and then it gives me all the time slices instead of having to manually type them all in. Then I'm going to load the snap file from the MDS Plus database. I almost always start with the EFIT02 ER. This is kind of our best attempt at the between shot EFITs using MSE data. So I find this is the best place to start. Once I do that, I just kind of leave the defaults. You can change from SER Quick to SER Auto, but it doesn't make too much of a difference on something like this is just using the rotation as a correction for MSE data. So there's not going to be a big enough difference for that to really matter. Yes?
Can you explain briefly the difference between EFIT02 and EFIT02 ER?
Yeah, sure. So EFIT02 uses MSE data that is like our, I don't know, not raw, but this is our calculation without any sort of corrections. But the MSE diagnostic is sensitive to ER in the plasma. It makes its measurement from electric field from the B cross B. So if there's ER, it also changes our measurement. So what we do is use the rotation from CER to estimate ER in the plasma and use that to correct the MSE data so that it's better. It's more accurate to what's actually from the B cross B term. So then I generate K files from the snap file. Okay, so then this is when you'll start to actually do the work that goes into making a kinetic EFIT. This allows you to do each step individually. So I always deselect the run equilibrium and work on run profiles first. I really like Tomage's quick fit tool, so I use that almost exclusively. One reason is it works really well and it's a great tool. Another reason is OMFit profiles tends to store a lot of data, and you end up with, if you do a whole time with maybe 30 or 40 time slices, you'll end up with projects that are multiple gigabytes that are hard to open and close. So these file sizes become much more manageable using quick fit. So you click in here. There's a question before about what happens at the edge. So the default is to stretch the Thomson profiles have 80 eV at the separatrix, and to stretch the CER profiles to match the impurity density to the electron density pedestals. So as I always select, or almost always start with EFIT02ER, I select that for the addition up here. And my time range was 2645 to 3145. I like to encapsulate that time range just to make sure I'm bracketing all the time slices I want. I'm not sure if that's super important, but that's what I always end up doing. And then I choose a time step that's going to match the time step of the diagnostic. I'm not typically interested in short time changes, whether it's elms or sawteeth. Most of the plasmas I have don't have sawteeth, but they have lots of elms. So typically just averaging through those sort of fluctuations. So since I'm using a large delta T time step, you get a lot of data to fit to. So I fit to it. I almost always use the defaults, but I also scroll through to make sure that the fit's working pretty well. So what I'm looking for is if there's any places in the fit where the fit's not tracking the experimental data very well. Like if you have too large of radial smoothing, or if for whatever reason your profiles change relatively rapidly, then you would want to change your time smoothing. And then kind of step through each of these. And then this, let's see, it's going to, all right. So this is something, this is rotation right here. And this is something that in the past has caused problems when I run kinetic EFITs, is if you end up with a negative rotation, sometimes that creates errors when you run trans. So I don't know if that's still a problem, but it definitely was a problem in the past. So whenever I'm doing these profile fittings, I make sure that there's no negative points in the rotation, especially because physically, I don't think there should be any rotation. And there's also some differences too, like we're using carbon rotation, and I know Sean's done a lot of work showing that main ion rotation is different than carbon rotation. So there's some subtleties, but I think in general, it's better to make sure that you don't have negative rotation. So as Tomás showed, probably in this case, since I played around with this a little bit before this class, I'll do this, but sometimes I'll change, like I'll zero the edge will help if there's like a small region near the edge with negative rotation, or I'll change the smoothing or time smoothing. In this case, I have to remove these points because I couldn't figure out another way to do it.
You have a question online, by the way.
Yeah, sure. Go ahead.
Yeah, this is Colin. I've never heard of trans having a problem with negative rotation, and it definitely shouldn't, right? There's not something wrong with negative rotation.
I've definitely had problems with negative quantities going into trans before.
Well, like negative, I mean, like it's very, if you have a negative main ion density, that'll throw an error from new beam and stuff like that. Right? I've seen that certainly, but not negative rotation. I've never seen a problem with negative rotation before.
Maybe
And
you're
there's
right.
no reason you can't have negative rotation.
True. Okay, yeah, probably you're right. But regardless, you shouldn't have negative rotation in a case like this, right?
I wouldn't necessarily agree with that. No.
Really? So you think that fit is legitimate when it goes like this?
Yeah, probably. I mean, within the parameters of the automatic analysis, I'm sure that's probably right. I doubt that it's something that wouldn't show up at least somewhat in the surfeit analysis as well.
So physically, what would happen to cause negative rotation at the pedestal?
Well, so rotation is a function of the torque and the transport, right? And then in addition, you're looking at just the outboard midplane part of it, right? So there's reasons that you could have 2D colloidal asymmetries in rotation, such that the outboard midplane could end up like lower in the first place than as compared to some sort of flux surface average or whatever you think. In addition to the fact that the torque is different there. Yeah.
So like similar to where you see tungsten rotation and you get like a shifting of the tungsten density, something like that happening with carbon. Is that what you're saying?
That's an element of it. Yes. But the net result is that it's not, there's no reason that it's not physical.
All right. Well, I'll believe you since you're the expert, but I have a lot of doubts.
But what I don't understand is this, and I guess this is a question for Tomasz too. Aren't there a bunch of green measurements where the fit profile is dropping below axis? Are those measurements?
Yes. And
So how come the GPR's confidence interval is really tight and it's doing a poor fit there and should be actually giving you a very large uncertainty?
Because the error bars of every single time points are very, very small.
Okay, so it's. But the
So the model itself is not able to reproduce data, and therefore it's underestimating the uncertainty. If you will increase the time resolution, you will resolve every single element, then the uncertainties will make more sense.
Okay.
This only because he used a very long time step, so the uncertainty is not really reflecting the reality.
Okay.
I mean, these measurements are real. The carbon 6 rotation, the carbon rotation can go negative. I know Aztecs looked at this, so I haven't paid that much attention myself, but I think one explanation is the pressure gradient of the main ions is actually helping to drive this, so the two rotations aren't really coupled as well as we would like. So
you're saying that it's likely the main ion rotation's positive, but
Yeah,
the carbon.
yeah.
So then as we're using the carbon rotation as the main ion rotation going into the transport codes.
That's probably the bigger issue really in my mind is that's going to be a problem for the analysis you're using. You're not really looking at transport of the rotation of the angular momentum, are you? But
No, I mean, in the end, I don't think this really affects the community very much. Yeah, Colin made a good point about this probably not causing the problem in trans. Probably negative densities would cause that kind of problem, which happens sometimes in these too.
yeah, I mean, it's annoying, but in a way, but it's real. I mean,
Okay.
I don't know where in the measurement we're making an error.
Well, I mean, so there's also the thing with the what is it? Is it the ion temperature in the scrape off layer also goes really high typically in these plasmas too? And I've heard varying interpretations about whether that's real or not too.
Well, Colin maybe could have some opinion. Well, no, I mean, our thought is this probably high energy, I mean, carbon ions hanging out there. I mean, the density is extremely low, and I mean, it's not really what we think that the main ion density is out there. And in fact, I think the hydrogen or the main ion measurements show lower temperatures out in the pedestal land. I don't know if there's many out scrape off layer.
Okay, yeah, go ahead. I can't see whoever has
That's
hands
right.
up, so yeah. Good.
So I guess I would just, add on to this that there are these questions out here that are very normal questions. But if you ask yourself whether it matters, you'll probably find that it doesn't, especially for kinetic E-fits, right? I mean, so if you say, is this rotation matter? Well, if you're doing ER, you want this rotation, you want the carbon rotation. If you're trying to get ER, because you're going to use that to correct MSE or something. But then again, you're probably not doing that with this tool. If you're trying to do momentum transport, then yeah, now you're in trouble, right? But that's generally also rare. And if you want temperature in the scrape off layer, you're also doing it wrong this way too. So there are questions here, but they tend to all resolve and like you don't need to actually care about it. The rotation, also comes into the carbon density calculation, but in a small way, such that when you're at the low values of rotation, it's not mattering as well. So if you're plus or minus 10 kilometers per second, it doesn't matter to that calculation to a significant amount. So usually the answer for workflows that involve kinetic E-fits is that you don't need to care.
Yeah, I agree with that. Rich?
Also, Devin Battaglia did some analysis with XGC on a QH one shot several years ago, and he found some of his, so that's like follows particle orbits, and that code crosses the separatrix, goes at open fuel lines. And, they found high values of temperature and rotation out there. It's able to match some of it, not all of it. So, I mean, yeah, it makes you uncomfortable, but, there's probably some physics, but we're not accounting for that physics in any of the analysis we do. So you kind of have to ignore those.
Yeah, it's hard. I mean, I believe that that's what you're measuring, but then how you incorporate that into the model is.
Well, we can't right now unless there could be a lot of XGC analysis to see how real this is and does it apply to all kinds of shots. But
okay, I shall go on. All right.
Thanks for bringing this up so we can air it a little bit.
I've had this conversation many times on some of these details, and I end up making similar mistakes about saying something about rotation, and then Colin corrects me, and you can correct me too.
I do kinetic E-fits by kind of the hand method and like trying to decide where the separatrix is relative to the ions. And I start seeing these things go bizarre and think, well, okay, the separatrix, they're outside the separatrix. So, I mean, yeah.
Yeah, and it really depends on the analysis. If you're very focused with the pedestals, some of these details are more important. I tend not to be as focused on the pedestal for most of my analysis. So sometimes I am, but typically I'm not. So, all right, let me try to, I have to get through all these profile fittings or I can't go do transport codes. So when I did this before, I think all these ones look okay. The Thompson data is pretty noisy for this shot, but the fits look all right. So when you're doing this analysis and you want to run 1, 2 or trans, You need to either do NC6 or Z effective, but you don't have to do both of them. So typically I just do NC6. Because the codes for D3D assume that all of your impurity ion is carbon. So based on the carbon density, you can calculate C effective that way. So either way is valid. So I'll just show you something here. You get like a little bit of divergence right here. I think this is something to look out for if you're being more careful about it. But I'm not going to worry about it right now. So once you do this, you can save to OMFit. You'll be able to see that it's saved. You go back here, you need to run profiles again. That will save everything from the quick fit module into the kineticEFIT module so that the data is available in subsequent steps. Then next, going on to EFITtime. For the first iteration, I don't change anything. There is one thing, like, so you can use MSE and correct MSE for the radioelectric field. So we already corrected MSE using EFIT02ER. If you also use this, the code is set up. This is one thing that I actually worked on, and as far as I know, it still works. If you do this correction, it works off of the original data and not the corrected data. So it should work. Although typically I don't use this because the full radioelectric field is dependent on toroidal rotation, poloidal rotation, and the pedestal gradient, any sort of pressure gradient, but the largest one's in the pedestal. We don't always have poloidal rotation. It takes a lot more work to get that. And so if you want a really good ER profile, you can use different tools to get that. And as far as the pressure gradient is important, but the MSE data in the edge of the plasma has very large, the spatial resolution is very poor. So you're averaging over between 10 and 20 centimeters, while the pedestal is only like 1 to 2 centimeters. So using this really fine correction in ER based upon the pedestal gradient isn't really appropriate for the MSE channels that we have in the edge of the plasma. So for this reason, I typically just stick with EFIT02ER and just go with that. If you want to do more detailed analysis, you can do the full ER correction and then use it to correct MSE. But in general, I think depending on what you're doing, you don't typically have to do that. So I just leave the defaults. I run equilibrium. Okay, and so what I'm looking for after I do this is I go to plot and I plot chi-squared as a function of time. And so in the settings here, you have this convergence error of 0.001. So this is your goal for each EFIT step, is you want to get convergence error less than that. So what I want to see is I want to go and check that it's reaching that value. If it's above this value for all the times, then there's something happening that I need to figure out. The other thing I check is that all of these values for the individual diagnostics, the chi-squared makes sense. So in this case, they're all about the same value. Having done this, MSE is typically going to be between like 5 and 15. Magnetic probes will be around 20 and the flux loops around 10. So long as you see things about in that range, then it's okay. If you see one of these diagnostics and they're 100 or even in 50 to 70, something like that, then you probably should try to figure out what's wrong. And that could mean that there's a probe that you need to take out or an MSE channel you need to take out, and that's causing some sort of problems with your fit. But in this case, everything looks okay. So go back to here, do 1. So this takes you from iteration 0 to iteration 1. Within iteration 1, you can now run transport codes. So as the first step, you run profiles. Your profiles runs this. My understanding is if I do this now, it maps the profiles from iteration 0 onto the new equilibrium generated in iteration 0. That's correct? No, it's not correct. So you should refit them onto the new GEQ disks.
Yes.
Okay. Well, so then what you would do here,
Just press the fit button and save it.
here. Okay.
Then you can change the time then.
Yeah, let's see. But we don't have a ton of time. I want to get to, but so you see the addition up here change from EFIT02 ER to EQ disk. So these are the EQ disks that were generated in iteration 0. And now you have the chance to fit your profiles onto those EQ disks. So next is to run transport. So you have two options for running transport. You can run 1.2 or trans. Typically, I like to run trans. The reason I run trans instead of 1.2 typically is because trans, I can account for fast ion diffusion, which I can't do. I think 1.2 has some fast ion diffusion, but I don't know how to control it within OMFIT. So for the steady state plasmas that I work on, fast ion diffusion tends to be quite large, and it really changes the beam deposition. I saw hands. Okay. The one advantage of 1.2 is it's much faster than trans. Trans, if you're running a whole shot, will take 24 hours. If you're running even like 500 milliseconds like I have here, it'll take a few hours. So you're not going to finish the analysis in a single session. So I tend to not change any of the default settings in 1.2 and then just run transport. This will only take a couple minutes, but it's a good time if anyone has any questions. Yeah, Wilkie?
If you're running trans for the average user, does that send it to PPPL and back, or?
Yeah, it sends it to their cluster. So you have to get an account with PPPL and then set up some things in the background so that you can show that you're a valid user of their cluster.
And then for the 1.2, it's anyone who has.
1.2, you have to send an email that goes to the computer group in Sterling to, I think, I don't know what it says.
Yeah, so, OMFIT has this concept of licenses, which at some point we're likely to get rid of, because there's no reason that OMFIT should have the license instead of being added to some Linux group on the cluster itself. So that email comes to me because I was the responsible officer of 1.2, not because I'm a member of the CSS group.
Oh, okay.
It should be changed to just us.
It's a report request for that.
Got it, okay.
Yes, Rich?
So the reason you're going through this step is to get the fast ion pressure, right?
No, I'm going through this step for two main reasons. One, you get a pressure profile that you can then use as a constraint for in the kinetic EFIT, and you also get a current density profile, which you are used as a constraint. So that's the big difference between regular EFITs and kinetic EFITs. The kinetic EFITs use the pressure and the current density profile from a neoclassical calculation. Typically, so MSE works really well in the core, but the resolution in the edge isn't as good. So you get these bootstrap current profiles in the edge that you use as constraints in the kinetic EFIT.
So I always wondered this when I'm making kinetic EFITs is why we should have the pressure profile from just from fitting the kinetic profiles, right? So like why can't we form, like, is it the main thing is the current density constraint? Because like in theory, couldn't we
The
form a
pressure profile is more complicated than you think a little bit because you have electron pressure, ion pressure, and fast ion pressure. So all three of those go into making the pressure constraint in the kinetic EFIT. So it's not as simple as just giving the Thompson pressure, for example.
Right, but if I had, one derated beam or something, then maybe I don't care. like that. I mean, I'm not saying
But
this
then
is.
you're probably not doing a kinetic EFIT if you just have like super boring plasma.
Who's to say that the current density is not interesting, even if, like, I could have ECCD? It was just a question of like, is it, what, I think you answered it though, we need both the.
Yeah, it's just, you need all the components. So yeah, after I run 1, 2, you can go into plot and plot the state files. So here's the current density profile. I'll show you this in a little bit, but basically you end up using the edge current density profile as the constraint, and then the temperatures and densities. But I'll show you what the pressure constraint looks like down here. So now at this step is the first time we're making a kinetic EFIT. So if we look, let's look at the current, because that one's a little easier to see. So here's the current constraints for the different times. So you see these parameters here, you can change where these points are. Each of these red points are the constraints that you're going to put into a new K file that's going to go into EFIT to calculate your new equilibrium. So what it's doing is you're biasing towards the edge because we don't have good MSE measurements over here, and you're using a prediction of what the bootstrap current looks like to get this current density profile. Sometimes I change this a little bit. If I feel like this is providing too much of a constraint, I'll lower this weight. But typically I don't change that too much. And then here's the pressure constraints. So you have total pressure, which that's going to be the electron and ion pressure, and then MBI pressure. So this is your fast ion pressure. So if you look in the core, it's like about 30 kilopascals compared to 130. So you're roughly like 20–25% of your pressure is the fast ion pressure. The one thing that I sometimes change on this, if you look, this includes the error bars. So you can see the error bars very well right here. But at the edge of the plasma, the error bars are very small. Sometimes when you're doing this, you'll end up over constraining the kinetic EFIT in the edge, and you'll kind of need to artificially increase the error bars for your pressure profile. So to do that, you would, the minimum pressure uncertainty, and you can increase that. Sometimes just going from 100 to 200 newtons per meter squared is enough to make it so your equilibrium fits better. Whoops. And then now I do make some changes here. So one, when you're doing kinetic EFITs, you typically want to get a really good equilibrium. The magic number everyone seems to put is 1 × 10⁻⁸ as the convergence error that indicates getting a really good equilibrium. So I put that as the goal, and then I increase the maximum number of EFIT iterations to 100, and then I run equilibrium. So if I go like 5 more minutes, that's okay?
Yeah.
Okay.
Anyone's free to leave if they want to.
I thought we were free to leave the moment we
Yeah.
stepped in.
You had some pizza. You had some pizza. You had to stay at least 10 minutes.
All right, so the kinetic EFIT's done. As I did after the end of the first time I ran the EFIT, I plot chi-squared as a function of time. Here, I'm looking at similar things. One, I'm looking at this Grad-Shafronov error and seeing if I hit 10⁻⁸. I did for 2 time slices. Interestingly, when I did this before this meeting, I only hit it for 1 time slice, which will go into what I'm going to show you next. But the other thing I'm looking for is I'm looking at the total chi-squared and making sure that none of these seem wildly off. Like I mentioned, the minimum pressure uncertainty, sometimes you'll end up seeing high chi-squared for pressure. If that's the case, then you want to increase the uncertainty because you don't want any one diagnostic dominating the constraints for the equilibrium. And this is, I guess I should have mentioned this when I was talking about the constraints, but one way I think these constraints really end up helping is that CER has some points on the high field side of the machine. MSE has a couple points on the high field side of the machine, but mostly we're focused with mid-plane measurements on the low field side of the machine, which a quantity like the current density is not a flux surface quantity. So you end up with different current density profiles on the low and the high field side or above and below the magnetic axis. When you add these constraints for the current density profile and pressure profile, you're adding constraints as a function of rho or size. So they're essentially colloidally symmetric. So these are like the first time that you're adding constraints to the high field side of the equilibrium, which just doing that is enough to make it so you no longer get like, without these, sometimes you get very large excursions of negative current density profile on the high field side. By adding these symmetric constraints, that takes away those kinds of things and it ends up smoothing out your current density profile, for example. So that's I think one of the larger effects that people don't necessarily appreciate when they're making the kinetic EFITs. So we get to this point and there's a really nice trick to get your Grad-Shafronov error lower for the times that don't have low Grad-Shafronov error. So this was something, I don't know, when I was making kinetic EFITs and always trying to get really low Grad-Shafronov error because everyone said it was really important. There was like an OMFIT coding camp and I was sitting next to Orso and told him about this and he wrote this script down here, which is called refine Grad-Shafronov. So if you hold control and hit enter, it brings up this, well, basically you can change the parameters that go into this. I always change this to false, otherwise it'll stop even if I don't want it to, and then press continue. So all this does is on these kinetic EFITs, it automatically chooses 7 spline points, 7 knots for your spline. And all this does is it just kind of jiggles those knot locations a little bit and then reruns the equilibrium to try to see what kind of Grad-Shafronov error you get. And as you see, after just one time, you end up getting that for this time slice. So typically the difference between having really good Grad-Shafronov error and having something that's not as good is just jiggling the knots in your fitting. Is very unsatisfying, especially because when I started this, people would spend so much time doing this and it was like sometimes it would work and sometimes it wouldn't. So I've also, like, I often use these kinetic EFITs as inputs into something like decon. I found that even if the Grad-Shafronov error isn't like 1 × 10⁻⁸, you still get similar results from decon. So I try to get a really small Grad-Shafronov error, but if I do this a couple of times and I can't get it some of the time points don't end up getting really good values, I don't kill myself trying to do it. So,
right. So the knots are where the constraint is actually imposed, is that right?
So there you end up having splines for FF prime and P prime, and the knots set kind of how those splines are formed.
Okay, but the effect of moving around the knots is still sort of moving around where your like spline fit points compared to different spots in your constraint profile, or I'm trying to understand what like
I think it ends up being more of a computer, like just machine error kind of differences are the differences between getting really low or not as low Grad-Shafronov error. I mean, you can see this time point here, it was like 10⁻⁴ for almost all of them. And then you have one that gets down to 10⁻⁸, and it's it's not moving those spline points very much, and that's the only thing it's changing as far as I know. Although I know that I can see this code's evolved a little bit from when we first worked on it. Yeah.
The definition of the Grashof error here is the real force error in the Grashof equations or the error in the Picard iterations?
Can you say it louder? Sorry.
Is it the Grashof error here really means the force error or the iteration?
So what it is each, maybe you guys can correct me, but my understanding is you get the Grashof-Ranoff equilibrium, and then you do the next equilibrium, and the Grashof-Ranoff error is the difference between the two equilibria.
So it turns out, because I was inquiring about this a few weeks ago, if it's tolerance and exit criterion, all of that is based on, the difference in the psi in the previous step versus the next time step. Basically, that's the tolerance it's looking for in the Picard iteration. So it doesn't do this right-hand side versus left-hand side difference. So
I've just recently wrote a script which you need there to calculate the actual Grashof error.
so it's doing the residual between
Yes.
the,
Also like updated.
the Orso script is doing that, or
No, it's not. It's simply just this difference between the iteration.
but what do you say? What did you say is there that's doing that?
There is another script which calculates actual direct difference between left and the right side of the Grashof error.
Do you know what it is?
What's it called?
One of the
Because
oldest
Torren
ones.
just wrote one recently, and
I have always been curious
Just
why it
go
wasn't.
down, it should be, maybe it's not there.
This
It's
is the
not
stable,
the stable
it's
version,
in
maybe it's still in unstable.
We can talk about it later.
Okay. Well, yeah, so I think this finished running, and as you can see, now you have all the time slices with Grashof-Ranoff error, 1 times 10 to the minus 8. So that's great. So at that point, so the typical practices are you can go into iteration 2, and now you have a whole new set of GEQ disks that you can remap your profiles to, and then do that. Again, I tend not to focus on the pedestal too much. So I think if you're more core focused and stability focused, I haven't seen a big difference between going through the second iteration and stopping after the first iteration. If people do this and can show me examples where it's very important, I would like to see it. But I've tested this, and I tend not to do this too often because I haven't seen it make a big difference.
So why, this is interesting. Why would you, in your case now, why would you believe in iteration 2? Because you ran Orso's magic
well,
respine.
yeah, so you've run Orso's thing, you get all these GEQ disks with really good Grashof-Ranoff error. So the idea is you then take your profiles and map them onto these new equilibria because they were mapped onto the old one. Then you run 1, 2 in snapshot mode where you're not evolving the current density profile. You're just going to, I don't understand exactly how that works, but you don't evolve it in the same way as the previous step. You just essentially calculate the current density profile from that and then use it as constraints into one more kinetic EFIT. But yeah, I don't do that a lot because I don't find it makes a big difference in my analysis. Yes.
So just to clarify, the 10 minus 8 here is the difference between basically whether it's iterations.
Mhm.
And so even though you get 10 to the minus 8, you could be on a non-global solution and your Grashof-Ranoff error could actually be larger. Okay, I just want to make sure. So effective, because what we care about is left and right side of the equation actually balancing, right? So
it is true, but typically this is what everyone talks about is this Grashof-Ranoff error.
It's really surprising that it's not there, but since it's a self-consistent framework, EFIT, right? So you could probably argue that because you start with a guess for J phi, that feeds back to your solution for psi at that iteration, that feeds back into your next guess for J phi on the right-hand side. Maybe you could argue that the residual is also small, but we're just, I don't know, Torren and I just started looking at this for cakes actually.
okay, I assume this is true also for Tom's tools as well, but it's the same, okay.
I thought it was a real Grad-Schiff-Ranoff error.
Yeah, that's what-
You
that's what
should
it becomes.
mention that to other people. It's not real, sorry. Rich.
Yeah, I don't really know the answer, but possibly, Phil Snyder used to talk about getting this error for running a lead on the pedestal for the pedestal. So for edge MHD codes, maybe it was a figure of merit, but yeah, I guess.
It's definitely for us too. I mean, John Farron would always tell us to get to 10 to the -8. Chris has always told me to do that because John told him kind of thing too, so.
In my experience, it's not the only metric. You can actually have a very, small error and then still have crappy fits, so.
Yeah,
At
definitely.
least with the pedestal stuff.
But I think what I especially wanted to show with using like that tool that Orso wrote is that the difference between having a really low Grad-Schiff-Ranoff error and not a very low one is just like small changes in those knot locations. So it's not like, I mean, it used to be like you do this and you're like, oh, it's not fitting well. I have to do a better job fitting my profiles, but that's not really the difference. The difference is just kind of these subtle differences in the equilibrium.
I actually have a great story to follow up on this. I don't know, Anthony Shing is online or maybe Severin, but they're running a bunch of cakes for us, for Rafi's FTP thing. And turns out the most recent way of running cakes was turning off the FitLZ, which is, I think, yeah. So it generated all these thousands of equilibria for us, and then we started looking at them, and you would have, based on the normal metrics, quality equilibrium, but when you usually inspected them, they were absolutely crap. Like, for a perfectly looking plasma, they would have horrible fits, sometimes even trying to fit into private flux or just like a small area in the core. So they had to turn back on. The FitLZ. So
Yeah, typically, like in the between shot EFITs, we leave it on. Sometimes if I have problems, I'll turn that off if I think that that's causing problems in the fitting. So, Kim?
So, another question is, so the number 7 for the node point is some sort of magic number as well?
Number 7 for.
7 knots on the.
Oh, that, I mean, so I don't know that it's magic, but it's just the default basis functions. It's just the default that goes into OMFit. You can change the number of P prime knots or FF prime knots. I believe that based upon your 1-2 current density profile, they choose the knot locations based upon that automatically. Will, you said? Oh, okay. All right. Well, I guess that's about it. If you want to chat afterwards, just feel free and talk to me. But thank you, everybody.
that you